All right, you are now ready for 4.3, which is going to be all about fractional exponents. So you'll notice in 4.2, we only worked with integer exponents, so whole number exponents, either positive or negative. It is possible to have a fraction in your exponent, so what we want to do today is talk about what does that mean to have a fraction in your exponent. And here's what it means. So if I have, switch colors here, a to the 1 over n power, so that integer is now in my denominator. I know what the integers in my numerator mean now, but if I have an integer in my denominator of that power, it just means the nth root of a. We use roots to undo powers, okay? So as you're looking at some examples here, we're going to create a list of some common squares, cubes, and other powers so we can understand these roots. So as you're looking at these squares, for instance, what you would be able to tell from this is that then the square root, that's kind of the most common root we're used to seeing, the square root of 4 is that base I square to get to 4, that is 2. But we can do other roots. We aren't just stuck with square roots. So like with 2 cubed, I can say, okay, then I can cube root 8, and I cubed 2 to get to 8. So the cube root of 8 is 2, and so on. The fourth root of 16 is 2. The fifth root of 32 is, of 32 is 2, okay? So that's what we're going to be looking at today. And some of the time, we're going to be able to calculate those exact roots. So we're looking at perfect roots there when we're looking at 4, 8, 16, and 32. 32 is a perfect fifth root. 4 is a perfect square root. Now we can do roots of any numbers, even if they aren't perfect roots, using our calculator as well. So make sure you can find that root key in your calculator too. But today what we're going to look at is simplifying these roots and simplifying then also these expressions with integer exponents and working with those. Turns out anything with an integer exponent also, all of those rules apply that we learned in 4.2. So let's just get used to these integer exponents first. So to have an idea of what some roots are going to be, let's look at some of these common squares and so on. So common squares, these are the ones we've seen the most throughout our lives probably. 3 squared is 9. 4 squared, and again, you can do this in your calculator, is 16. 5 squared is 25. 6 squared is 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. And 10 squared is 100. Okay, so we would want to be able to recognize that 9, 16, 25, 36, all of those are perfect squares. We also want to recognize a few perfect cubes and so on. And we're going to do a shorter list of these because they grow so fast. So 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. And I'm just going to stop the list there. We'll just focus on those for now. We'll also look at 10 cubed though. Powers of 10 are nice and easy because it just adds a 0. So 10 cubed is 1,000. We'll also want to recognize that 1,000 is a good cube, is a perfect cube root, okay? We'll do fourth powers as well. So if you plug in 3 to the 4th in your calculator, you'll see that's 81. 4 to the 4th, 256 is a perfect fourth root. And 5 to the 4th, we'll see how big we get quickly here, is 625, another perfect fourth root. For 10 to the 4th, we'll look at 10,000, which is another perfect fourth root. Powers of 5, 3 to the 5th, we would want to recognize that 243 is a perfect fifth root. 4 to the 5th, 1024 is a perfect fifth root, and 5 to the 5th is 3,125. Now you do not have to memorize these, right? Because we can make this list pretty quickly using our calculator, but just to make you recognize what exactly we're doing when we're rooting. So anytime we're rooting, we're undoing that power. So if I take the fifth root of 100,000, I get that base, which is 10. Okay? So we're going to practice with that in both forms, in both the form of the root as far as the fractional power and as far as the root. So we're more used to seeing that root probably. So what I'm going to do is say, okay, I see 4 to the 1/2. What I want to think in my head then is, okay, that's just the square root of 4. And typically we don't end up writing that 2, right? When we have square roots, we'll leave that 2 off there and just have the root without any number because that's our most common root. And recognize that, oh, 4 to the 1/2, that's just the square root of 4. I know that I squared 2 to get to 4. So 4 to the 1/2 is actually just 2. If I see 8 to the 1/3, looks weird, but okay, I know what that means. It's actually the cube root of 8. I want to know what did I cube to get to 8. So I can look at that list of perfect cubes there and I see, oh, I cubed 2 to get to 8. So that this answer down here is 2 as well. There's something interesting that happens with negative numbers too, so I want to look at that. On this one, we're thinking, okay, what did I cube to get to -27? So if you look at your list of perfect cubes, you can see here that you can cube 3 to get to 27. So if we want to get to -27, we must have taken -3 times -3 times -3, excuse me, to get to -27. So the answer here is -3. However, when you look at the square root, this here, right, with that -1/2 would be the square root of -16. I don't have any options that work. I know the square root of 16 positive is 4. But if I take 4 times 4, I get 16. And if I try and make it negative, it doesn't work because 2 negatives becomes a positive. So -4 squared is 16. So it turns out I cannot take the square root of a negative number. The answer here would be not a real number. Okay, and that'll happen with any even root because all those negatives will pair up and cancel out, and there'll be no way for us to end up with a negative number in it. So we can do it when we have odd roots because those negatives won't pair up and cancel. We'll have one left over. But if we have an even root, then we get not a real number anytime we try and root a negative number if that root isn't even. Okay, so we're going to use that now that we know that to finish this out. Get rid of that line there. All right, so looking at your list, can you see what would be the 4th root of 625? So you look at your list, under 4th roots, you look for 625, and under 4th roots, we see it right there. We must have taken 5 to the 4th power to get 625. So the answer here is 5. One we maybe don't recognize and one where that list is helpful. On the next one, we see a negative number, so that should be a trigger for you to say, okay, am I looking for not a real number or will this work out? And we see an odd root. This is the cube root of -125. So we're in good shape. We know that our answer will definitely be negative then, and then we just look for the cubed root of 125, which would just be, going up to your list, the cube root of 125 is here, and we end up with a -5 to make sure we get a -125 in the end. On number 7, we see another negative number. We check our root, and immediately, since that is an even number, it's a 4th root, we know we cannot take a negative number and take an even root. So this is not a real number. The last one there is just another good practice. Looking at your 5th roots, what did we take to the 5th power to get 32? Looking up at our 5th roots, we took 2 to the 5th power to get 32. So here we have that the answer is just 2. So when they're perfect roots, we can just think about that number we took to the 5th power. We can identify that number if it's a perfect root, or we can realize that it's not possible and not a real number. So to summarize those rules there for you, if we have a positive number under our root, then we're good to go, right? We always know that we'll get an answer. And in fact, the nth root of whatever that number is will always be a positive number. But if whatever we're trying to root is negative, then we know we're in good shape if n is odd, if we're trying to take an odd root, and we know then that we should get a negative number for our final answer. If n is even, if we're trying to take an even root, then this is not possible, and it is not a real number. All right, so getting into roots, understanding, okay, we're looking for what we took to that power of the root to get to the number under the root. So the other thing that we can do is if we have factors inside of something that is not a perfect root, but the factor is a perfect root, we can start to pull those perfect roots out because we have these rules for roots and also for exponents, okay? That if I have the same root, I can multiply under that root, okay? So if I have something like the square root of 12, I could break that up into any of its two factors, something like the square root of 4 times the square root of 3. And what we're going to start to see is, oh, then I can actually take the square root of this perfect square number and simplify this first expression. That's what we're going to be working on now that we have that rule. And the same thing also applies with division. If I have division, I can break up that division into dividing into the top having a root and the bottom having a root. Okay? So a good example of that here would be, okay, what if I have the square root of 20 over the square root of 4? Well, I don't have to think about simplifying those separately. I can think about that as the square root overall of 20 divided by 4 and actually carry out that division to get something like the square root of 5. So I don't have to break them up or anything like that. I can just simplify inside of that root if it's division or multiplication. The last thing I want you to realize is, again, so long that a is positive, because we know things get weird when we have a negative under our root. But if a is positive, what's happening? An nth root undoes an nth power. So if I take the nth root of a to the n, it just drops both. They cancel each other out, and I end up with just that base. So here, a good example of this is, okay, what if I have the square root of 7 and I square it? Then the square root and square undo themselves and I end up with 7. Same thing if I have 7 squared and that's all under the square root. It doesn't matter in which order I do roots or powers because they're both the same thing, and I end up with, again, 7. Those things undo themselves. Okay, so what we want to do is use those rules to simplify some radicals. Okay, and this takes a few steps. So the first thing we want to focus on is, okay, what do we do when there's just a number to simplify a radical? And by this I mean, again, we want to break up 48 if it has any perfect roots in it. So you're looking for 48 to be divisible by anything that is a perfect square. So you'd be looking for it to be divisible by 4 or 9 or 16 or 25 as we go down that list. Okay, these are all of your perfect squares. We are looking for one of those to possibly be a factor of 48. So you take 48 divided by 4 and you will see that 4 works. But if you keep going down your list, you'll see that 16 works as well. So we always want to use the biggest factor. If you don't find it right off the bat, that's okay, you'll recognize it later, but always look for the biggest perfect root. So if you take 48 divided by 16, you'll see, okay, this is the same thing as 16 times 3. 16 times 3 is 48. By that first rule we just saw, we can break this square root up, and then I can actually take the square root of that perfect square. So the square root of 48 is the same thing as 4 times the square root of 3, which we will write like that. And that is my simplified root. The rest of my root 3 does not have any perfect square factors, and I just leave only the numbers that are not perfect squares underneath the square root. Okay, so let's try that again. I'm actually going to go on to number 3 next. And then we'll go down to number 2. Let's stick with the square root and just add in, okay, what if we have a variable to an exponent underneath there? What happens? So let's deal with the number first. Let's start by breaking up 50. And in our list, we can see, oh, okay, 25 is a factor of 50. That leaves me with 2, and 2 has no perfect factors, perfect square factors, okay? So we can break 50 up like we did 48, but then what do I do with x to the 6th? Well, think about what's a perfect square as far as a power of x. And x squared is what is perfectly squareable, right? X squared and a square root would cancel. So we want to see how many x squareds are in x to the 6th. So here I have 2 x's multiplied together. Now I have 4, and I can keep going. Now I have 6 x's multiplied together. So I've got all my perfect square factors that make up x to the 6th. And now I just want to, again, break each one of these up. So square root of 25 times the square root of 2 times the square root of x squared times the square root of x squared times the square root of x squared. Everything can be broken up separately that's being multiplied together. And we see all of our perfect square things here. 25 can be square rooted, x squared can, and each one of these x squareds can. So we end up with 5 times x times x times x, because all those squareds and square roots cancel. And then we're just left with times the square root of 2. So our simplified expression is 5x cubed square root of 2. And we're done. Okay, this takes a little bit to get used to, so let's keep going to a few more examples. Here's another one with just one number and one term that's exponential, but this time notice we're taking the cubed root this time, okay? So we're looking for perfect cubes. So in our list of perfect cubes, we have that 8 is a perfect cube, 27, 64, 125. So we're looking to see if 625 is evenly divisible by any of these. Test them out. You will see that 625 is perfectly divisible by that. It ends up that 625 is 125 times 5. Now we're looking for perfect cubes. So as far as x to the 4th goes, we have to think about, okay, then x cubed is perfectly cubable. And how do I get to x to the 4th now? Well, I just have one more x, so that x is what gets left behind. So I break this all up. That's the cube root of 125 times the cube root of 5 times the cube root of x cubed times the cube root of x. Now again, this is perfectly cube root and this is a perfect cube root. So what do we get? 125 as a perfect cube root, when I take that back down, is 5. X cubed, cube rooted becomes x. So we've dropped the roots because we've actually taken the cube root. What's left on the inside of the root is a 5 and an x. So we make the root and we put them back together. 5 and x need to also be left under the root. And this is our final answer for number 2. All right. Last one here, maybe pause the video and give this one a shot. We have a fraction here. Just remember, you can handle all of these separately. Okay, so we can think about this being the square root of y to the 5th, the square root of x to the 7th, and handle all of them separately. That means anything that's squared as far as a variable goes is what we can perfectly square root. So you want to break it up into however many squares we have. So thinking about the top, the numerator first, I'd have y squared times y squared. That would be 4 y's, so I'd have 1 left over to be y to the 5th. As far as my x's go, I'd have x squared. Definitely going to need a little more space here. There we go, x squared. There's 4, there's 6, and I'd have 1 left over to get to 7. And z squared is already good to go. I can handle my numerator separately from my denominator. 25, we don't need to do anything with. That's already a perfect square number. W to the 13th, and we're going to have a few W squareds here, right? There's 4 W's, 6 W's multiplied together, 8, 10, 12, and 1 left over. Okay, so you're going to pull all those squareds out. We're actually going to square root all of those squared terms and pull them out of then the square root because they will have already been square rooted. 25 is also included here. So outside of the square root, I have y times y. I have 3 x's multiplied together and 1 z. I'm also going to handle that denominator at the same time. Actually, let's do that next. Okay, so on the top, that's what I can pull, and you'll see you have a y and an x left inside the root. So that can be yx or xy, however you want to write that. All right, on the bottom, I have a 5 that comes out from the 25. I have 1, 2, 3, 4, 5, 6 w's multiplied together. And I have 1 w left on the inside of that root. So as I think about simplifying this all the way back down, here's what we want to give in the end. Y squared from these 2 y's, x cubed from these 3 x's, z. On the bottom, without the root, I have a 5, and I have 6 w's multiplied together. Then we like to put the root back together separately out here. All multiplied by xy is left on the top under the root, and w is left on the bottom under the root. And that's a good final answer there. Now you can imagine as we get to bigger powers, even w to the 13th was kind of annoying to write out. So can you see the pattern of what's happening here? Notice what happened. We had y to the 5th, and we ended up with y squared on the outside and y on the inside. So what happened to y to the 4th here when it came out? The 4 got divided by 2 to become 2. X to the 6th on the inside, maybe a different color there, x to the 6th on the inside divided by my root of 2 to become 3. W to the 12th on the inside, there's 12 w's there, became w to the 6th on the outside. So we have a rule to help us with this simplification. The rule is that if I have a fractional exponent, this is the same thing as dividing that root and that power, right? The power of 12 got divided by 2 to be 6. So this is just, if you have m over n, m is your power and n is your root. Sorry, that kind of looks like y to the n. Let's see. 1 over n, and n is your root. Or you can think about the root, whoops, goodness. Or you can think about the root and then the power. It doesn't matter how you think about it, okay? But we have same thing here, the nth root of that base to a power, or the nth root of the base to the power. What you want to realize here is that if you have a fractional exponent, it's just the power over the root. Power over root. So we can have all kinds of fractional exponents like 4 to the 3 over 2. What is that? Oh, it's 4 cubed square rooted, power and root. Now, actually, the way I've written this, I would actually simplify this the other way around. A root will make a number smaller, a power will make a number bigger. It's harder to root to find the root of bigger numbers. So since it doesn't matter what order you do this in, I would take the square root of 4 and then cube it. Those two things are equal. That's easier because we know the square root of 4 is 2, and then it's easier to cube that smaller number 2 instead of trying to cube 4 from the beginning. And we see that 4 to the 3 halves is actually just 8. So something that looks fairly confusing as far as the notation goes, we know how to do it. It's just a 2-step problem. Do a power and do a root, typically doing the root first and then the power. So try it with these next ones and see what you get. Maybe pause, try it, and then open it back up again to see how it went, okay? With this one again, think about the root first, 125, that's a cube root, and then square that number. That would be a power of 2/3. 125 cube rooted. Make sure you look at your list and find out what that is. The cube root of 125 is 5, and then that's what needs to be squared for 25 to be your final answer. On number 3, you'll take the 4th root of 16 because we have a 4 in our denominator, and then you will cube that. The 4th root of 16 is 2, and when I cube 2, I get 8. So again, that fancy expression, we can simplify it down to 8. Don't get confused on this last one. The power is negative. What does it mean for a power to be negative? It means I want to divide by that term, and once I create the division, the power is positive. Then just think again about, okay, that just means the square root of 25, because the denominator is 2, being cubed. 1 over all of that, since I started out with a negative exponent up there. Okay, so in the end, we end up with 1 over the square root of 25 is 5. That then needs to be cubed, and my final answer is 1 over 125. Again, you're going to get a lot of great practice with this in your homework, working with fractional powers, working with simplifying these roots, all kinds of things. One thing I do want to note at the end of this is that you can do all the same things that you did before with your rules of exponent. You can do those with fractional exponents now. So in this section, we learned what fractional exponents are, but 4.2 and 4.3 come together. So you're going to see some on your homework that this will be helpful to know. So let's say I had something like x to the 3/2 over x to the 1/4. Well, I can just use, I don't have to think about, okay, square rooting x and then taking it cubed. That doesn't make sense because x isn't a number. I just want to simplify this exponential expression using the fact that this is a quotient. So my quotient rule would say, oh, this is x to the 3/2 minus 1/4. And I can take 3/2 minus 1/4, do it in your calculator, or think about the fact that you need a common denominator. This is the same thing as x to the 6/4 by taking 3/2 times 2 over 2 minus 1/4. Oh, this simplifies down to just x to the 5/4. And that would be your final answer because you can't actually take x to the 5/4 power. If it was a number, now we could simplify it and take that number, the 4th root of it, the 5th power if it had a perfect 4th root. Okay, but you can use those same rules we were using in 4.2 when you see fractional powers to help combine two exponential terms that are either being multiplied, divided, taken to the same power, right? All those different rules that we have. So give that homework a try and use those Zoom sessions or your email to get a hold of me if you get stuck on any problems. You also have the answer key to all of those problems, so make sure you're checking your answers as you go and that you're understanding it. All right, guys.